Hello and welcome once again to our nice little podcast here called Post Cloud, where we talk about all things cloud and cloud future and what are we doing with this stuff and who's trying to sell you what rubbish this week. My name's Chris Krantz. I'm a bit of a cloud guy, as I often say, and I have lots of fun talking to my co-presenter, Stephen.
Hi, I'm Stephen Howell. I am growing to be a cloud guy, messing with Kubernetes a lot these days, but also have a ton of history with real iron infrastructure. A lot of this is going to be cloud and how we got to cloud and what it means to move things from what you used to have onto what you have now. Because this week we're going to be talking about Iops and storage side of things.
IOPS has still been one of those things that has plagued me over the years and continues to plague me. When you're standing up EC2 instances and stuff, sometimes you're asked for what types of disk you want or how many IOPS you want if you're choosing certain types of disk. So, Stephen, I'm wondering, can you give us a bit of a background as to what IOPS are? Why do they matter?
This starts with the definition of performance, and a lot of people define storage performance as how many gigabytes can I move from A to B in a certain amount of time. And that's some of the picture, sure. But when you're doing workloads for large applications, that tends to be less important because most of the time you're going to be looking for a record in a database or a specific file, and you're going to be reading that data, updating it, writing it. And so what you're looking at is the time taken to turn around an input or output operation, a read or a write. And so IOPS are input output operations per second, right? So the definition of an IOPS has been used for a long time, and we tend to measure them in a number of different ways. We look at the kind of throughput measurement that you might be familiar with, copying stuff off of your memory card. And we would call that a sequential operation because you've got a large amount of data and you're taking all the blocks off that disk, 1, 2, 3, 4, 5, 6, 7. And then we have a random operation. And in that, you're taking these tiny little records that are each individually quite small, and you're not taking them any fixed order. So you might be jumping around, like starting at block 3, then going to block 7, then back to block 1, and so on and so forth. And these are two very different workloads. Historically, when we looked at spinning disks, it was all about trying to make everything look like a sequential workload because the disks were fundamentally really bad at doing random. Because you had a piece of mechanical reading apparatus, the disk head, that would actually have to move from one point on the disk to another point on the disk. And the time taken to swing that little arm with a little reader and writer head on the end from one point to another, it was a large amount of the overall operation. For a very long time, it was difficult to do random operations because a hard disk is going to give you a couple of hundred, even if you're spending thousands upon thousands.
You're talking there about the kind of how delicate hard drives actually are, and I think they seem like they're pretty robust things. But there's a great video of some guys like in a data center shouting at their storage array, and you can actually record the latency increase as they shout. They're not touching the array at all; they're just shouting at these disks, as many of us like to do.
It's a mechanical device. It's a very finely tuned mechanical device, and it's resting on this layer upon layer of assumption. And then we saw NAND devices start to appear, like the memory cards in your cameras, but taken to the level where they can function as real disks, and they had the wear tolerances and throughput to go up against hard drives. And then we saw them rapidly overtake and go from a couple of hundred IOPS per second up to maybe like 50,000 operations per second. But then people discovered that what they could do to make it even more efficient was to take the flash that they had in a SATA SSD, and they could take that flash and connect it directly to a PCI Express bus in a computer. You're treating this disk like it's a graphics card or a network card or even a piece of memory. With PCI Express Gen 5, they're now up at like 128 gigabit per second, just ludicrous speed. So we've seen this kind of massive evolution, and you take this to cloud, and all of a sudden you have all these plethora of decisions that are rooted in a history of storage, and you're thinking, oh, but I just wanted a database. I want fast access to my data. How do I have so many choices?
An interesting analogy which kind of helped me get my head around the difference between IOPS and stuff and the difference between kind of sequential and random access stuff. And it is thinking about it like a waiter in a restaurant. You've got a waiter in a small restaurant with lots of small tables, say a waiter servicing two tables at a time. That waiter can flick between those different tables really quite quickly, and sometimes they might stack up multiple orders. So you have one tray, hit right. I got 10 different drinks on this tray. I can just go and serve 4 or 5 different tables at once, but in a kind of a sequential way. So that waiter seems like they're operating really fast, but they're doing very very random things across those different things. Flip that over to a waiter dealing, maybe at a wedding or a large party. You've got a table of 20, 30, 40, 50 people, and you can't do that level of random access. You can't do those random patterns. But so what you do is you come in and you take everyone's order at once, and then you go away and then you serve those orders at once. Now, the actual taking and serving those orders en masse is much much quicker. If you do one table of 20 versus 10 tables of 2, you'll be taking those orders much quicker. A lot of IO is relatively random because you've got all these access patterns, because you've got this idea of lots and lots of users hitting it at very different times, all doing slightly different things.
On a desktop, everything should ideally be a series of sequential operations, and you can kind of make it that way with a bit of massaging. Whereas you get to any sufficiently complex system that's got multiple users, and it almost always disintegrates into looking like random IO because every user is doing something slightly different to the next user.
And applications have a ton of background processes that happen and are writing IOPS even when you've got no users on the systems. Starting to kind of scratch the surface of the problem here. But I used to work as a consultant. I was working for a .com, I guess you'd call them, but it was after the .com boom. It's in the 2010s. Despite the fact that being an online presence and being relatively modern in a lot of the front end and a lot of the middleware they were doing, the back end was a relatively monolithic, big old traditional SQL database. They had so much data in there, and it was a lot of it was active data because they had such a wide portfolio that was always being queried and read and so on. To get the performance they needed out of there, they had to put in some dedicated PCIe cards, dedicated flash in there, and they had multiple of these cards in order to service the performance they needed. What you'll find is that as you start pushing any kind of drive, really, whether it's a mechanical spinning drive or a flash drive, the IOPS profile sometimes it's relatively flat. With what happens with spinning disks is that you have this curve. So as you start hitting the limit of what a spinning drive can do, the latency increases. Latency is the response time. So how long, if I request something, how long does it take for that to reply back? Steve was talking earlier about disks are typically 10, 20 milliseconds. Flash devices are sub-millisecond, generally always going to be sub-millisecond. That's where we start talking about nanoseconds and so on. What you'll see is when you get that latency bump, suddenly memory starts to spike, CPU starts to spike because the rest of the system starts to have to play catch up. It's caching more, it's doing more CPU cycles, trying to work out how do I get this data in a place that's going to make the disks perform better. So they invested really heavily into these SQL database clusters in order to support the front end of the application and the middleware and everything else. And there was an interesting solution to that. When they were doing a migration into public cloud, a lot of their applications into public cloud, we looked at these databases, whatever cloud service it is, you size the instances, relatively easy to do, in order to size those dedicated flash-based drives that we needed to drive the disk performance for those systems. They were going to cost $30,000 per node per month. So that project to migrate the databases was quickly mooted.
We've kind of learned with cloud that if you're trying to deal an application to anything beyond a medium-sized business, even large businesses, let alone countries, you can't just buy a bigger computer. The problem happens when you are now turning around the I/O paradigm from the old one with spinning disk to the fastest flash drives that are now operating so fast that DMA is slowing them down, and they require at least one CPU core to be running. It will create a toll. That's taking away from your application, and it's inefficient. And you can put a certain number of these drives in and have them managed by a CPU, but no more.
Put that into kind of some real world context. Everyone's talking about AI these days. But if you think about a machine that needs to use AI, you need fast network access because you need to read and write from the system. So you're going to have a relatively high speed network device. You're going to need a lot of storage because you've got that data, the large language model that you need as the data backup for it. And it needs to be rapid access because you need to be able to get access to it. So a large number of these NAND or PCIe attached flash drives. But you also need a bunch of GPUs. because that's where a lot of this machine learning and the neural network computational stuff happens. And the GPUs are definitely competing with those PCIe attached storage devices for the amount of PCIe bandwidth you need. So you have to start using this scale out, fan out architecture where you have multiple smaller boxes, maybe you have two GPUs, maybe you have 4 to 10 drives in them, maybe less even, and then a single or dual network interfaces. So this architecture becomes an architecturally, like a hardware architectural challenge in literally how do we build these servers to cope with the workloads that we're talking about. And AI is one of those perfect storm problems where I need all of these different components in order to perform and do what I need to do. Most systems don't need that combination. If you're using a big old database, you probably don't need a GPU in a database server. But it is one of those challenges that we've got right now, especially as people are going out and looking at, okay, love ChatGPT, but I don't love my data in it. So let's start building this stuff in house. And it starts becoming an architectural challenge. And this is why we're seeing some people come out with custom kind of AI built hardware.
So if we want to increase our Iops, we add more servers. But there's also some other patterns that influence that. We want to increase our Iops, but say we're the team that supports this application. Do we want to come in on the weekend? The old model where we had one server running our workload, if that thing went down, we got some alarm, we had to hightail it, go fix the thing. Now, when we look at cloud, is that going to work? Because all of a sudden it's not even a 9 to 5 in our local country. We could be running an application that people are using the other side of the planet. So we need to find an application architecture that lets us run multiples of these nodes and lets them fail gracefully, stops disrupting our application when we inevitably have to sleep, because sooner or later we'll have to. And so we move from this single large server and we gain throughput and our IOPS capacity at the same time as we also gain resilience, which is massively underrated. But as a support team or someone trying to run a cloud project, it's useful to know that it's there. And sometimes you can hide it away behind, say, DynamoDB or something else where someone else is holding the bag. And if it fails, it's their problem. But every now and then, and especially if you're trying to take a large volume of data and put it in house, you have to consider what happens if one of these things breaks.
The next challenge is really, there's different scenarios why you might need to know this in terms of scaling your existing systems. I've got an existing application, I need to scale this out. Maybe you've got a traditional database that you can't scale out, so you're going to need to scale it up. Where you've got an existing system that I'm growing for some reason or other, they're probably the simpler scenarios to deal with, because I'm going to look at what is the IOP profile that exists today, and then I'm going to extrapolate out. Now, there's some underlying overhead you've always got to that, but if you need to deal with twice the users, you're pretty much going to double the number of IOPS you've got. Add some headroom into that, and you'll be fine. The complication that I've always come across is you go and talk to the application team, and they're building something new. So maybe they've refactored an exact application, so it's exactly the same as the existing application, but it's fundamentally changed in what it does. So back to my story about the .com I worked for, there was a project there of migrating some of the data off of that traditional SQL system and moving it into a NoSQL system. Great. The access pattern completely changes because you're now dealing with a document. For them, it was dealing with a document store. And so understanding about what that looks like. So what is going to be my IOP profile for that application?
The one place you don't want to be in is finding out after it goes wrong. I knew a team who were moving from a physical server onto a virtual machine. They were doing this for a credit card processing system, and they decided just to fire it up and go. And they came back after the weekend to find that they had something like $17 million of unprocessed credit card invoices that failed SLA, and they lost a very large customer. You need to look at this and do some testing. And like Chris was saying before, you don't want to test it up to the bleeding edge. You want to test it to the point where you don't start to walk the fine line between it being okay and latency falling off a cliff. So what you typically do is run things flat out and see what the burst limit is for your absolute throughput, absolute number of IOPS. And then you'd limit the IOPS down to maybe 80% of that to give yourself a little bit of headroom in case something stutters. because if something stutters and you're running at 100% throughput, it's going to fall over. And so you take a pragmatic compromise, you find out where the limit is, and then you just back it off till it's safe. And you could do this with a test harness. You want some repeatable transactions, so record some sample data, run it through. You want to make sure that when you do the testing, you're actually hitting the underlying storage as well. So a lot of the time when you're trying to do IOPS, you're not going to be hitting that storage because the operating system and the application stack knows that that storage is slower than main memory. So what it's going to do is whenever you've got any free main memory, it will keep data in memory. So if you try and read files from a disk, the first time it reads off the disk and gives it to you, it moves that file through memory while it's giving it to you. And then if you ask for it again, it doesn't go to the disk again because it's already moved it through memory and left it in the cache. So it just fetches it straight out of memory, which is great news for your response times, but terrible news if you're trying to gauge what really happens for storage. So you need to test it with a set of working data that is larger than the memory in the machine typically. So if you've got your 64 gig server, you find a working set that's comfortably in excess of that, and know that if your server has 64 gigs of memory and your application is using 8 gigs of that, it's probably going to take the other like 56 gigs and just use it to cache your file data. Just assume it's going to do that because pretty much all modern OSs will do that.
Writing those test harnesses is doesn't have to be complex, but is often something that is deferred or not immediately thought of. Depending on your application profile, you can release it and see how it works there. There is the concept of canary testing where you release something and only siphon a certain number of users across to it. It'll help you profile the application with live data, but a very small subset of live data. So if it does go wrong, you're only affecting a small number of users. Now, not all applications can do that. If you're doing a web application, then actually that is quite a common thing to do. That can be a really effective way of testing the sizing requirements of that as well, because you'll take. It's not just about the success. There's lots of benefits to do canary testing, but one of the things you can get out of that is to start getting the performance profile, and then you can start extrapolating that.
Part of the reason why you might have something like canary testing is that you've gone from a single on-prem physical instance of your application and you've re-architected it so that it can work in the cloud, so that you're in a position where those are options to you. And a lot of people who have on-prem databases do not have the option to easily transition from that world into one where they've got cloud features. And one of the biggest hurdles there is to choose a good time to re-architect your application. Because if at this point you've got this three-tier application, your web server, your application server, and your database, and that's been in existence since, say, the early 2000s, chances are it's built on a pattern that is not going to scale when it hits cloud.
Some of these refactoring projects or these cloud digital transformations, as we've talked about in previous episodes, projects, you don't need to do everything at once, and actually try not to do everything at once. There's nothing stopping you from building a cloud architecture in your physical bricks and mortar data center. This is where we talk about cloud native patterns. Is you can build something that is cloud ready and then move it into the cloud because you reduce the number of moving parts. There are people that successfully re-architect everything and go straight into the clouds. Of course, you can do that, but you are making a rod for your own back. You're making things potentially more risky and complicated than they might need to be. Kind of reminds me of a job I had a while ago where I was reevaluating the data center contracts. And the clock was ticking for me because I kept on saying to the CTO, look, we've got 18 months before this contract ends. If we don't make a choice in the next 6 months, we are not going to be able to migrate off. 12 months is probably about realistic for most people to move out of a data center. And I think a lot of people don't actually work backwards, create a work back plan to work out, okay, this is the end of my contract. How much work do I need to do to be confident that at the end of my contract I can switch things off? And I think that's why we get into these mad rushes, last minute rushes to say, right, sorry, we need to move everything to the cloud. Let's bring in some consultants. Let's bring in some contractors. Let's all hands to the pumps. We need to go and do this by next week.
You've got to consider if you're changing the execution environment, if you're changing the application architecture, and if you're changing any of the kind of code in the application as well, That's a new application. That's not a migration. You don't expect that to just run first time. If you're taking something that you'd already containerized on prem and you're now running it in public cloud, you can make some assumptions about how that's going to behave, because I think Kubernetes has become this universal common denominator that enables you to transition a workload from a laptop to a data center to public cloud and have mostly the same workload and have that predictable behavior where you could do some scaling on your laptop that worked over in your data center that still works when you put it in cloud.
There's some interesting ideas when you go into certain cloud instances. You can choose NVMe backed cloud instances, but depending on the options, the NVMe might be non persistent. You kind of almost get IOPS for free. There's limits, of course, and you're paying it for the actual underlying instance. But some of that non-persistent ephemeral drives that you get in those are really high performance. So depending on your use case, depending on what you're doing, you can use those drives. But then you've got the option of the different types of drive you can add to it. In most cloud providers, you've got different types of drives you can add. Most of them still allow you to add traditional spinning disks. Depending on your workload, they're really, really cheap and very, very cost effective for obvious reasons because they're quite cheap and easy to do. A lot of the newer generation stuff, they're not building them into the data centers anymore. You're probably getting to the point where you're choosing generally between some kind of SATA or SAS attached flash device or some sort of NVMe attached flash device. The NVMe attached stuff is going to be higher performant, but also more expensive. The SATA/SAS attached flash device is going to be a little bit more cost effective, but lower performance. So you need to make these decisions as you're going through and architecting these applications. With certain cloud instances, you're also going to be choosing, literally, you're going to be saying, I want a guaranteed number of IOPS. That's not to say that's not your maximum. That's my guaranteed minimum that I'm going to get delivered to this application. So be careful when you're sizing your applications there. Don't size your guaranteed to your maximum because you want to make sure that's what my base is doing, and then can I spike above that? Because you'll always have these lumpy access patterns. It's just the way of the world. So you want to make sure that you can spike to the point which is acceptable to your applications. There's an architectural decision you can make in terms of building the application and where you put the high performance stuff and whether that is highly volatile or something that needs some core persistence. You want your guarantees on failure after failure.
You've got kind of a number of dimensions here. You've got obviously financial costs, it jumps into most people's minds. You've got performance, you've got the reliability, and you've got kind of your cost as a human being, as an engineer, as an architect, how much time you put in to develop that. So you've got, the enterprise storage arrays, enormously financially costly, kind of okay performance profiles, a lot of maintenance required, but give you peace of mind and resilience. And then you've got, going to cloud with some local NVMe drives where things might break. It's reasonably hands on, or you could maybe buy someone else's software defined storage like Amazon's EBS. There's a lot of compromises you can make, and I guess you need to figure out where your strengths lie as an individual or as a business. We've looked at a whole bunch of different storage use cases. We've talked about some storage technologies. We talked about how you can measure those technologies. And the important thing, I guess, is really at the end of the day to make sure you understand your use case, to make sure you understand how many IOPS you need to get by, and to make sure you understand how many the system can give you. And once you've got those two figures, you're in a better place, right, Chris?
100%. And to add to that, that to help you get to work out what your IOPS profile is, you want to start. It's all about the ultimate. Ultimately, all of this is about user experience. Work out what is that user experience you want to do, even if you're just setting an internal uncontractual SLA in terms of this is the response time, this is the availability, this is the failure rates I want to serve up to my users, and then work backwards in terms of, okay, what does that mean for my IOPS profile, my IOPS requirements, my scale up, my scale out, my data architecture, all these things we talked about.
Just make sure that what you're gunning for is feasible and realistic.
Thank you very much for joining us. I hope today was good. I hope today was interesting. As always, give us a like, give us a thumbs up, give us a subscribe, all those things you do wherever you're watching this.
If you want to add us to your favorite podcatcher, then you can find us on Apple iTunes, on Spotify, or a good old RSS feed on Pocket Casts. See you next time.
Thanks a lot, folks. See you again soon.